Sometimes you might not have conjugate faults, but you might have an extension fracture and a fault that form at the same time or in the same stress regime. So what I'm going to show you here on this stereo net is how to work out where sigma 1, 2 and 3 are given a fault and an extension fracture. So here we have plotted a fault and its pole and an extension fracture and its pole. And I've also taken the liberty of plotting in dashed line here a profile plane to the intersection between these two structures. It's so easy to find sigma 1, 2 and 3 if you have a fault and an extension fracture. The extension fracture gives you so many clues. Now first of all, the intersection between the fault and the extension fracture is sigma 2. The next thing to remember is that extension fractures form perpendicular to sigma 3. So all you need to do is find the pole to the extension fracture and you have sigma 3. So I'll just turn this so that the extension fracture is lined up on a great circle and you can see where the pole is. Here's the pole to the extension fracture, and that is sigma 3. Now the only other piece of information you need to know is that sigma 1 also lies in the plane of the extension fracture. Now if you know where sigma 2 is, sigma 1 has to be 90 degrees away from it in the plane of the extension fracture. So if you've got the extension fracture lined up on a great circle, you can just count 90 degrees away from sigma 2. So here's sigma 2 and count 90 degrees. 10, 20, 30, 40, 50, 60, 70, 80, 90 here. And that'll be sigma 1. Now it lies where the profile plane intersects the extension fracture. So now we've got the stress regime sorted out, sigma 2, sigma 1, sigma 3. The only thing left is to work out the slip vector on the fault. The rule of thumb is that the slip vector is defined by the intersection between the fault and the profile plane, or we give it a special name, the movement plane or the M-plane. So here it is here. The other thing to recognize is that the fault and the extension fracture make an acute wedge, and that wedge always moves into the intersection between those two features, or the sigma 2 axis. Now it's not the extension fracture that has shear on it, but it's the fault, so you can put an arrow on the fault to indicate this wedge moving towards that intersection. Now that will help you in determining the shear on the slip vector. Now I'm just going to move the fault back so that it sits on a great circle. There it is there. Here's the center of the net, and if I think of this slip vector on the fault, I can imagine a line. Ignore that one, that's for another example. That slip vector makes a line like this. This would be the dip slip. That is the slip vector. And I have to bear in mind this arrow for the hanging wall. And this is the hanging wall to the fault. So does the hanging wall move up to satisfy this arrow, or does it move down? And if you were looking down on top of my hands here, you would see that it has to move down. So the hanging wall has gone down, and the footwall to that fault has gone up. I'll just turn this back so that north is lined at the top of my stereo net, and that is my shear sense. I'll draw my little arrows in here to help me out. This is an oblique slip fault. It's got a lot of dip slip on it, but it also has a little bit of left lateral strike slip.